Okay, so we're going to take those ideas from that introduction to linear programming and apply it to word problems. So the step we're going to be adding here is that we want to form our objective function first, or really the order of this doesn't matter, but we're going to need to form the objective function, and then we're also going to need to gather all of the constraints. So what I actually like to do best with these is start at the end of the question. So at the very end, it's asking me how many acres of each crop should the farmer plant to maximize profit? I like to start with that last sentence because often that question really helps to set up all of the pieces for your objective function and the constraints, or it'll make clear what your objective should be and what and then everything else will be the constraints. So in this question, we have two types of crops. I'm just going to set some variables. So X is going to equal crop A. It'll be acres of crop A? Yeah. And then Y is going to be acres of crop B. So for the objective function, what we're going to use is profit. We're interested in maximizing profit. So I'm going to have an objective function that's P equals, and then I need some information in terms of how is profit calculated based on crop A and B. So let's go reading in the problem itself, and we're going to do a few times reading through. So we have a farmer's going to divide her 50-acre farm between two crops. Seed for crop A costs $10 per acre. Seed for crop B costs $20 per acre. And the farmer can spend at most $700 on seed, so that's also dealing with cost. If crop B brings in a profit of $150 per acre and crop A brings in a profit of $140 per acre, all right, there's our information for putting profit together. So my objective function, we're getting $140 per acre from crop A, so I'll be 140 times X. And then we're going to add on the profit from crop B, which is 150 per acre, so 150 times Y. So my objective function that we want to maximize is going to be P equals 140X plus 150Y. All right. There's our objective, and we're going to put that to the side and work on the constraints. Okay, so putting the constraints together, if you want to, you can start with the fact that we should only have positive values coming through. So X is going to have to be more than or equal to 0. Y is going to have to be more than or equal to 0. So that's in there. That can just be implied by word problems, even though they don't specify it. Okay, she's going to divide her 50-acre farm between two crops. So what this will do is where we have the number of acres of crop A plus the number of acres of crop B, that should be less than or equal to 50. Doesn't necessarily say she's going to use you'd think she'd use all of it, but we're just going to say less than or equal to 50. Seed for crop A costs $10 and crop B costs $20. So 10 times X plus 20 times Y gets at our cost. And the farmer can spend at most $700, so that needs to be less than or equal to $700. And then that's all of our information. So we got our objective function, which is to maximize profit. The constraints, X and Y need to be positive. X and Y need to add up to less than or equal to 50. And then for the cost, 10X plus 20Y, that needs to be less than or equal to 700. So that sets up those pieces. Now what we're going to do is graph these linear inequalities. So what I'm going to do is set up an X and Y axis. And let's see, we know we'll be in the first quadrant, so I set up my axes to be in the first quadrant. X plus y is less than or equal to 50, so really we're graphing y is less than or equal to 50 minus x. So with that, we'll have a y-intercept at 50, and then a slope of -1. I'm going to go ahead and grab those intercepts like I've been doing. The intercepts will really help with graphing here. So x and y, where x is 0 or y is 0. If x is 0, then we're graphing y equals 50. If y is 0, then x is 50. That's nice and easy. Okay. Then we're also graphing this 10x plus 20y is less than or equal to 700. I'm going to use the intercepts for this too. So x and y, if x is 0 or y is 0. So if x is 0, we have 20y equals 700, which will be 35. And if y is equal to 0, x will be 70. Okay, so we have some coordinates to graph there. So for my axes, let's see if I can do jumps of 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, just high enough on the y-axis. And that's what I needed, right? Yeah. And then for the x-axis, we can go a little further to get up to 70. Okay. 60, 65, 70. I'm just going to go a little beyond. Okay. So for y is less than or equal to 50 minus x, so we have our 2 points, 0, 50, and 50, 0. And then we're just going to connect those with a nice straight line. And then we have, let's see, 0, 35 is here. And 70, 0 is here. And then we're going to connect those two. All right. So for both of our functions, we're graphing below those, so less than or equal to, and then we want x to be larger than 0, y to be larger than 0. So this is another case where we're ending up with this corner trapped in here. Now, I know a lot of our examples are going to be this kind of corner trapped by the origin. That's not always the case. The other scenario would be out here beyond our lines and kind of going off to infinity. So it would be an unbounded feasible region. And actually, we're going to see that in this next example. So I won't give too much away with that. We'll see it there and what we'll do. But sometimes it's trapped between pretty much 4 corners. It could have more corners, but we'll see other scenarios too. Okay, so the corners. We have our origin 0, 0. We have the smaller of the y-intercepts at 0, 35. We have the intersection of the two, which is occurring at 30, 20. And if you're ever not sure where that intersection is occurring, what we can do is, let's see if I have enough room here. Because where it's going to be happening is where these two equations are equal to each other. So it's like if we had x plus y equals 50, and 10x plus 20y equals 700, it'd be solving that system of equations. So let's say I did elimination method here. I'm going to multiply that top equation by -10. So -10x minus 10y equals -500, with that 10x plus 20y equals 700. So those x's cancel out. We'd have 10y equals 200. Divide by 10, so y equals 20. And then to get x out, we would just do, let's see, x plus 20 equals 50, so x equals 30. So if it's ever unclear where that intersection point is occurring, you can do solving of system of equations using those two constraint inequalities, just changing them to equations to solve. Okay, and then our fourth corner is coming from the smaller of the two x-intercepts at 50, 0. Okay, so our coordinates, we have 0, 35. We have 0, 0. We have 30, 20. And we have 50, 0. And what we want to do is with each of those, we want to maximize that profit function, P equals, what was it, 140x plus 150y. So we're going to take each of those coordinates and plug it in to calculate P. So at 0, 35, P would equal 150 times 35, which is 5,250. At 0, 0, we'd have a profit of 0. At 30, 20, we would have 140 times 30 plus 150 times 20. Which is 7,200. And then at 50, 0, P equals 140 times 50, which is 7,000. So we want the one that maximizes our profit, and that's coming from that 7,200 at that coordinate 30, 20. So what that tells me is that she would have a maximum, so the farmer would have a maximum profit of $7,200 with, let's see, 30 acres of crop A and 20 acres of crop B. So from the solution, we get three pieces of information. We get our x coordinate, we get our y coordinate, and then we also get this maximum value coming out from plugging into the equation. All right, this video is going to be long because we have another example. So feel free to pause and take a break here, and then we'll start dissecting all of this information. Also, you could try this one out, like pausing the video and trying this for yourself could be good to see where do you get stuck or where are the issues popping up, things like that. Okay, so again, I like to start at the end of the question. So the final sentence says, in order to minimize cost, how many servings of each dried fruit go into the box of bars? So our objective function is we want to minimize our objective function, and we want to calculate the number of servings of each dried fruit, which let's see. So we're going to have x and y, each being servings of, and let's see, we have apricots and dates. So let's do x is apricots and y is dates. So we're going to want, let's see, oh, and we're trying to minimize cost. So for the objective function, let's see where cost comes in. Ooh, right here. Dried apricots cost $9.99 per pound, which is about 3 servings, and dried dates cost $7.99 per pound, which is 4 servings. So for apricots, if x is representing the number of servings, it's like 1 serving. So what we're getting is this ratio. So we're getting $9.99 for about 3 servings. So what I would want to do is take that $9.99 and divide it by 3 so that I get the cost per serving. So that's going to be $3.33 per serving. So for cost, we're getting 3.33 times x. And then I want to add on the same thing, but with y. So with the dates, it's $7.99 for 4 servings. So $7.99 divided by 4. And that's going to be a decimal, but since this is money, we'll just round it to 2 decimal places. So it's going to round up to basically 2. So we're going to do 2.00. So $2 per serving for dates. So we had a little adjustment to do there so that we were doing per serving instead of for the unit of pounds. So 2.00y. So our objective function is to minimize cost, which is 3.33x plus 2y. Okay, so that takes care of our objective function. Let's talk about the constraints. So we are forming a box of 10 fruit bars. Decides to use dried apricots, which have 407 milligrams of potassium per serving, and dried dates, which have 271 milligrams of potassium per serving. And we have that information about costs that we're going to skip over. The company would like the box of bars to have at least the recommended daily potassium intake of about 4,700 milligrams. So actually, I'm going to write that out right now. So let's see. For potassium, okay, constraints. For the potassium, we have 407 coming from apricots, plus 271 coming from dates, and we want the intake of about 4,700. So we have at least 4,700. So we want that 407x plus 207y to be more than or equal to 4,700. All right. And contain at least 1 serving of each fruit. So x needs to be more than or equal to 1. So that serving of apricots needs to be at least 1. Y also needs to be at least 1. And that's it for our constraints. So we have that constraint of the amount of potassium. Then we also have the constraint of how many servings we want, at least 1 of each. Okay, so let's start graphing. So let's set up our x and y axes here. And let's see, I'm going to do units of 2. It's going to help, especially, so like graphing x more than or equal to 1 and y more than or equal to 1, that's not going to be too bad. This potassium equation, I'm going to use the intercepts to help me graph those. So let's see, when x is 0, we would have 271y equals 4,700. So 4,700 divided by 271 is, let's go 17.34. Just round that to 2 decimal places. And then for if y is equal to 0, so we'll have 4,700 divided by 407, and that's 11.55. So I'm just going to graph this as best I can. So with that, so I'm going to do units of 2 along the x-axis and y-axis. Okay, so having x more than or equal to 1, so that would be a vertical line at x equals 1. And then we'd want values larger than that, so we would be shading to the right-hand side. Y more than or equal to 1 is the horizontal line at y equals 1. And we want values larger, so we would be shading above that line. So it's kind of like our origin shifted in a way with these other examples where we were trapped at 0, 0. Now we're trapped at 1, 1. So just kind of bump those over because of those minimum constraints. Okay, let's graph this potassium equation. So 0, 17.34. We're just going to estimate that at about there. And let's see, 11.550 is about there. And we're going to connect these two dots. And we want where that linear function's larger, so we would be shading above that line. So what we have here is we're going to the right of x equals 1, we're going above this line that we just graphed, and we're going above y equals 1. So our region is actually above those three lines going off to infinity, like I was mentioning in that previous example as a possibility. So what's happening here is this is called an unbounded feasible region. But our process doesn't really change. We still want the corners of this. It's not going to be a nice polygon. It's not going to be trapped inside, but we still have these corners. We have this corner where x equals 1 is intersecting with that potassium equation. We have this corner where y equals 1 is intersecting, and that's it. Those are our two corners there. So let's talk about finding the value of those corners, because that'll be hard to do. Well, we know what our x and y value is. For this first case, we would have that x is equal to 1, and we just need that y coordinate. So what we're going to do is, if we have this 407x plus 271y equals 4700, what happens when x equals 1? So 407 plus 271y equals 4700. So subtract 407 for 271y equals 4293. Divide by 271, that's a 15.84. So that gives us our y coordinate there. So we're going to have a corner of 1, 15.84. And then our other corner is a similar idea, except we have y equals 1. So I'm going to do is the same thing, but we'll have 407x plus 271 equals 4700. Subtract 271 from both sides for 4429. Divide by 407 to get 10.88. So our other corner is 10.881. All right, so we have our corner pieces. So now we're going to see what the solution is. So we have one of the corners is 115.84, and we have 10.881. And we want to minimize the cost equals 3.33x plus 2y. So for our first corner, we're going to take 3.33 times 1 plus 2 times 15.84. And that's going to be a 35.01. And then we want c equals 3.33 times that 10.88 plus 2 times 1, right? Same thing. And that's going to be a 38.23. Now, we've had a lot of problems where we were maximizing, so just keep in mind that we are minimizing here. So we want the smaller of those two costs, which is going to be that cost of $35.01, which is coming from that corner of 115.84. So just going back, this is where, like, once we get those values and I know algebraically what my answers are, I like to go back to the question itself to know that I'm answering it correctly. So in order to minimize cost, how many servings of each dried fruit should go into the box of bars? Well, we would want 1 serving of apricots, 1 serving of apricots, 15.84 servings of dates. So to minimize And we actually have the cost here, so I'm going to include that to minimize to a cost of $35.01. They need 1 serving of apricots, and 15.84 servings of dates. Okay, I know this video was long, but with these, it's just helpful to go through these examples and just being able to get these equations out. Again, I find it really helpful to start with the objective, and that usually comes through in that last sentence. You might have to go searching for other information in the body of text in order to form that objective, but it's kind of a nice starting point, and it also gets me in the mindset of what we're looking for as well. So starting with that objective and then just reading through and grabbing everything else for the constraints, which will just take getting these pieces to come together. And then it's about graphing that system of linear inequalities, getting that feasible region, getting those corners of the feasible region, and evaluating with that objective function.